Alrighty folks, so here we are, section 7.3. Section 7.1 and 7.2, they go over the application of vectors. You might find those a little bit applicable to you, more so if you're taking a physics course, but they are not in the curriculum, so we're not going to spend our time on those questions in here. Now, we have already worked in this course, we've already worked on adding vectors, and we've already worked on subtracting vectors. We've also worked with our ability to multiply vectors, but really we've only multiplied vectors by a scalar quantity. So today we're going to jump into one method for multiplying two vectors, and we call this the cross product. Now, this is, the dot product. This is not the only way to say multiply vectors. So we won't use that terminology too frequently. We'll have to be very specific when we're talking about what we're doing. What we're calculating in this lesson is the dot product. Now, a dot product on the whole is a way to measure how well two vectors work together. And that really means, I guess, how much two vectors agree. So if we consider two vectors, then we would say that they work a little bit better together if their directions are similar. All right, so we would say that they work independently from one another if their directions are completely different. So if I think of two directions that are completely different, I might not even be thinking of something like north and south, but I might be thinking of something like north and down, or south and left. Those are directions that are completely different. We would consider two vectors working against one another if their directions are opposite. And that's where we're looking at a north or south, or up or down, or left or right, forward, backward, that kind of thing. Now, if we're going to compare their directions, how one vector's direction compares to the direction of another vector, then what we're really talking about is the angle between the two vectors. So for convention, what we do is we put the vectors tail to tail to one another to determine how well they're going to work together. So I'll move this vector over here. Good. It should look something like this. Tail to tail, we have two tails together down here. This is what it's going to look like if we're working with a dot product. Now, in here, then I'm going to be focused on the angle between the two. So the angle between the two vectors would look something like this. We could call it angle theta. Now, what we really need, okay, so we would say something like this is two vectors that are working relatively well together. These two vectors, their directions are not opposite. The directions are not independent of one another, but these two directions are actually relatively similar. Now, that's all well and great. If I move my my second vector, if my second vector, my blue vector, looked something like this, then these two vectors, you might notice, these are heading more off in different directions. And I know it sounds a little bit wishy-washy. More off in different directions. Yeah, well, that's what's going on. Their directions are a little bit more different because the angle between these two vectors has increased. Okay, so since these two these two vectors are now pointing more in a different direction than in a same direction, and what I mean by that is that really there's no overlap in the directions. Even if the vectors look something like this, there's a little bit of overlap in the directions, because if I'm considering a north, south, east, and west directions here, then what I'm looking at for my red vector, it goes straight east. But my blue vector goes north and a little bit east. And since there's that overlap, since it goes a little bit east, that's what we would consider they're working in the same direction a little bit. But if one vector goes straight east, and the other vector goes to the northwest, then there's no overlap in these directions. We would say that they're working against each other. And these terms are going to be wishy-washy. So if I have, there we go. So here, this would be the most two vectors can work against each other. If one points to the east, the other points to the west. Here, I would say that my two vectors are still working against each other. And here we would be able to define, let's see, we're okay. we would say that these two vectors are still working against each other because there's no overlap. One is going southwest, the other is going east. But as soon as I cross this southern line, so actually here, if I point this straight south, one of the directions is going east, the other direction is going south. Is there any overlap there? No, there's not. If one is going directly straight south and the other is going directly straight east, there is no overlap. We would say here, this is when we would say that these two vectors are working independently from one another. All right, but if as soon as this vector crosses just the tiniest bit east of south, then we would say, okay, these vectors are working together again. All right, so we're just coming up with a little bit of an idea right here. All right, so let's consider, we'll consider this this red vector as a stationary vector, if you will. The blue vector we'll play around with. So we'll keep track this time of what I was saying as I went through. Okay, so if my blue vector looks something like this, then we say they're working together. So we're expecting a positive product. If my two vectors are working against each other, like over here, we're expecting a negative product. If it's way up here, then I'm expecting no product because the two vectors, one of them is going straight north, the other is going straight east. There's no overlap. I'm expecting a product of 0. If you're following along with some of this logic, that's great. If not, that's okay. You'll get some more hard rules for you to work by in a little bit. If the two vectors, are working directly opposite one another, then we're expecting not only a negative dot product, but a really negative dot product because they could not be working more against each other. All right, so down here we're still expecting a negative dot product because if my blue vector is pointing down here, they're still working against each other, and then again, as I work, if my blue vector is pointing to the south, I'm expecting no dot product, or rather a dot product of 0. And then lastly, if I'm working under here, then yes, I do have a pretty significant angle between the two, right? If I go around this way, but still the directions are relatively similar, so I'm expecting, a positive cross product. Now you might recognize a little bit of what I'm doing here. If so, great. If not, then bear with me, you'll get there. All right, so we're working here, and if I consider, bear with me folks, I'm hoping that the puppy can keep her barking down to a minimum here. What we're looking, all right, let's kind of make a bit of a graph. All right, so if my two vectors, then we'll test one more. If the two vectors are headed in the same direction, then according to a similar logic to us before, we'll expect a positive dot product, but not just a positive dot product, a really positive dot product. We'll expect it to be, I don't know, close to its maximum. So let's try and put something in here. Okay, well, how many degrees? We'll still work in degrees as our advanced functions crew catches up with their work in radians. How many degrees is it all the way around a full circle? Well, all the way around a full circle, that's 360 degrees. If you like to work in radians, then we'll say that's 2 pi radians. Okay, halfway between 0 and 360 degrees is 180 degrees. That is pi radians. Fantastic. Okay, halfway between this 180 degrees and 0, I'm working with 90 degrees. I'm working with pi over 2 radians. And over here, I'm working with 270 degrees, and that is 3 pi over 2 radians. When you're giving your, when you're showing your work in this course, I don't, at this point, until the other folks have caught up with us, then I'm not going to worry too much. You can work either in radians or degrees, whichever makes you comfortable. So we're looking right here, and we'll say, okay, hang on. If my two vectors are heading in the same direction, then I'm expecting a maximum. Okay, and then that's great. And from where theta is 0 degrees, and that's saying they're headed in the same direction, to where theta is 90 degrees, it's positive. But then as soon as it hits 90 degrees, then I'm expecting a dot product of 0. All right, you might see where I'm going here. And then I'm expecting my dot product to go into the negative values because my angles do not overlap with one another until it reaches its minimum when our angle is directly 180 degrees or pi radians. All right, we'll keep going, and then we're expecting it still to be negative, but less so, reaching to 0 when our when we're working at 270 degrees or 3 pi over 2 radians. And as it gets towards 360 degrees again, then our directions are very, very similar, and we're expecting a maximum. So what kind of a shape, folks, did I draw right here? You may recognize it right here. I'm hoping you do. This, in general, we see some overlap with our cosine function. So that is the key to what that is one of the key pieces to what we're working with here. That idea that we're going to work with a cosine function, because according to the theta values, which is along our horizontal axis right here, according to our theta values, then it should go from a maximum, then our dot product should go from a maximum at 0 degrees to a minimum at 180 degrees, and then back to a maximum at 360 degrees. That's what we're looking at right here. Fantastic. Okay, so if we're considering a dot product, then we need to work with our cosine function. Now, we'll also, though, need to work with the magnitudes of both vectors. And let's consider a little bit what we know about multiplication. If I were to assess your knowledge of multiplication before this course, then first of all, I'm sure it would have been less in-depth understanding, and that's okay because you hadn't needed to delve into stuff like this. But with multiplication, you know a few things. If you multiply 0 times 3 or 0 times 8 or 0 times 100,000, then your product is 0. So a product of a 0 value is 0, but rather if we're looking to at two values, we'll call them, I don't know, A and B. If A and B are both bigger numbers, then we're expecting a larger product. If A and B are both smaller numbers, then we're expecting a smaller product. Or rather, if we keep only one of these consistent, let's say B is, I don't know, 3 or 1 or a 100, whichever. If A increases, then the product increases. If A decreases, the product decreases. And that's a little bit of the key that we're looking at here. So what we're really concerned about, as well as our cosine function, which will help us find our dot product, what we're also concerned about is the magnitudes of both vectors. So putting all of these ideas together, our dot product, and I'm sorry, I think that took me like 12 minutes to get to, but our dot product that we're working with right here is going to consider the magnitude of the first vector, and that's going to be multiplied by the magnitude of the second vector. And then we're going to multiply that as well by the cosine of theta. So that way, okay, well, hang on. Let's say, for example, our dot product is 0. Bear with me. I know that's not going to be very meaningful to you right now, but it will be in the future. If our dot product is 0, then one or more of three things is happening. Either, if our magnitude of AC is 0, then we would have 0 times the magnitude of AB times the cosine of theta. And it doesn't matter what the magnitude of AB is or what the cosine of theta is. This would equal 0 because one of the factors is 0. Good, so either, if our dot product equals 0, then either AC equals 0 or AB could equal 0. If AB equals 0, then we're in a really similar situation where we have the magnitude of AC times 0 times the cosine of theta, which would still equal 0 because one of the factors is 0. And the third way that we could get our dot product to equal 0, AB, is if the cosine of theta equals 0. Now, where does the cosine of theta equal 0? You should be a master of this, whether you've taken advanced functions before or you're taking it right now. Cosine of theta should be 0 if your theta equals 90 degrees or pi over 2, or your theta equals 270 degrees or 3 pi over 2. Those are the only two ways for your cosine of theta to equal 0 if we're considering an angle in between 0 and 360 degrees, which makes sense given the context of our problem right here. All right, so if the cosine of theta equals 0, that means that theta is equal to 90 degrees or 270 degrees. Now, what does it look like? What would we be expecting our sketch of our two vectors sketched tail to tail? What would we expect that to look like if our theta is equal to 90 degrees? Well, if our theta equals 90 degrees, by definition, we have a right angle in between them. All right, what if our theta is equal to 270 degrees? We still have a right angle in between our two vectors. So the only way to get a dot product equal to 0 is going to be if your two vectors are perpendicular to one another, if your two vectors are 90 degrees different in terms of their directions. Now, if you followed that, great. If not, that's okay. You'll see it all in practice in just a moment. So let's consider here, we have two vectors. Our two vectors are vectors v and vectors u. They have magnitudes 5 and 7, respectively. So we'll say vector v has a magnitude of 5, vector u has a magnitude of 7. When these two vectors are placed tail to tail, they have an angle of 60 degrees or pi over 3 radians between the two vectors. So let's start off and we'll sketch our two vectors. We'll sketch vector v. Vector v has a magnitude of 5. All right, if vector v has a magnitude of 5, maybe I'm looking at something like, whoops, I thought that was an arrow. Oh my goodness, it's not. That's all right. We've crashed it. We'll get there. We didn't crash it. We closed it. There we are. All righty. So we're going to have this vector v. I'll label that with a v. Good job, us. And then we're going to have vector u. Vector u is slightly shorter than vector v, so we should be showing that. Good. This is vector u, magnitude of, whoops, did I do those backwards? I did. That's okay. We have the advantage of hindsight. So we're changing our labels into v because v is the shorter one, and u down here. Good stuff. Now what we have right here, we're told that when we place them tail to tail, they have an interior angle of 60 degrees or pi over 3 radians between our two vectors. All right, so if we're going to calculate u times v, then what we're looking at doing is working with, according to our dot product equation right here, we're going to work with the magnitude of vector u times, and really I shouldn't use a dot there, I'll just write times the magnitude of vector v times the cosine of theta. So here I'm working with the cosine of 60 degrees, or the cosine of, or u v times the cosine of pi over 3. Fantastic. So if that's the case, all right, well, I know the magnitude of vector u. The magnitude of vector u is 7. So that means I'm working with 7. The magnitude of vector v is 5, so I'm working with 7 times 5 times the cosine of 60. Hang on, do I have any methods for evaluating the cosine of 60? Yes, you do. You have it from your grade 11 trigonometry or from your advanced functions trigonometry, and you should be there in your advanced functions course. In fact, I know some of you are, so let's go for it. Let's evaluate the cosine of 60 degrees or the cosine of pi over 3. You should be able to handle something like this. How do we do it? With one of our special triangles. You need to be able to sketch your special triangles from memory in this course. So we're working here. We're jumping right into it. We're not wasting any time. This is side length 2. This is side length 1 because it was 2 and then it was cut in half. This is then side length the square root of 3 from our Pythagorean theorem. Good job, us. All right. Well, this interior angle is 60 degrees or pi over 3. And that interior angle is is 30 degrees. Let's try and fix that. We're doing okay. There we are. 30 degrees or pi over 6. That's our special triangle. I don't care if you're using degrees or radians at this point in the course, but we will all transition to radians at some point. So if you're feeling comfortable with them, please use them. All right. So I need to evaluate the cosine of 60 degrees. All right, I know how to do that. The cosine of 60 degrees, well, I know the cosine is equal to my adjacent side over my hypotenuse. Fantastic. I know my adjacent side to 60 degrees. I'm working with 1. I know my hypotenuse is 2. So the cosine of 60 degrees is 1 over 2. That means the cosine of pi over 3 is 1 over 2. I'm working here with 7 times 5 times 1 over 2. Easy, I know how to evaluate this. That's 35 divided by 2. Well done, folks. You have just evaluated your first dot product. Give yourself a pat on the back, pause the video, take a celebratory spin, grab some water. You're feeling good. All right. Now what I'll ask you folks to do is try to evaluate v.u, not u.v, but v.u. Try it out, see what you come up with if you're trying to evaluate this particular dot product. Pause the video, try it out, and then come back. Good, so your work might look like mine, but also, honestly, it might not, and that's okay. Either way, you should get the same answer. There's a possible chance that you played around and you took your superior understanding of trigonometry and you wrote the magnitude of v times the magnitude of u times the cosine not of 60 degrees, but of 300 degrees. Because you caught on, you were smart, you evaluated that, but you recognize that the cosine of 300 degrees is actually equal to the cosine of 60 degrees. You get the same answer, 35 over 2. No matter what your approach, we're here. Now, if you like to stick with 60 degrees, and that made a whole bunch of sense to you, fantastic. I'll ask you to let your mind wander for the next 30 seconds. If you wanted to work with 300 degrees, I'm going to give you a bit of a shortcut. We can always consider this other angle, and that is the opposite side around our oh my goodness, I'm blanking for words as I teach this. The other way around between the two vectors. And if we go check on our cosine function way up here, you might recognize, all right, you might recognize if, bear with me here, if we're working at 0, and I need a better color, that's okay, we're getting there, fantastic. If we're working where theta is equal to 0, then that actually gives us the exact same output value, cosine of theta value, as if we're working with 360 degrees. Or if we head into, I don't know, say 45 degrees, that gives us the exact same cosine value, if we're working with 315 degrees, which is the opposite way around our circle. And you might see where I'm going here, 315 degrees. No matter what, as we keep going through, it does not matter in which direction we head taking our measurement for theta. Either way, we're going to be working with the exact same values. So if you wanted to use 315 degrees, that's fine, go for it. You're going to get the same answer. If you liked using 60 degrees and if none of that made sense, that's okay, don't worry about it. I'm hoping actually it does make sense, but we're not really going to use that idea as we go forth. Next, what I would like you folks to do is look at a dot product of u times u. All right, so if I'm working with u times u, then first of all, I know that the magnitude of u is 5 units. All right, and I know the magnitude of u is 5 units. So then all I'm looking for is the cosine of theta, where theta is the angle in between my two vectors. All right, well, if I'm working with u times u, hang on, let's copy this, let's bring it out here. We have a brand new vector to use, fantastic. And what happens is I place them tail to tail. And they actually end up, and I'm just going to leave it just slightly off of tail to tail, they end up almost on top of one, well, really, they do end up exactly on top of one another. So we would say here that these two vectors, their directions are working, these two vectors together are working very, very well, very strongly together. I'm expecting a significant dot product, as in a maximum dot product, because my cosine function I'm expecting to be maximized. So what's the angle between these two vectors u and vector u? Well, there's no directional difference. So if there's no directional difference, then my theta is equal to 0. All right, so my theta is equal to 0. Well, hang on, if my theta equals 0, then I'm working with the magnitude of 5, the absolute value of 5 times the absolute value of 5 times the cosine of 0. The cosine of 0, if you're not sure, you can show this, and really we should be showing our work. We can sketch that in here. Now we know, and this will be review for some of you, you will need these skills as you work through here. We know that if we set a terminal arm right here, with a unit circle, we would have the coordinates. Ooh, that's not a very good unit circle, I apologize. we would have a unit circle something like this. The coordinates I'd be working with would be 1, 0. Now I know in a unit circle, my coordinates x, y tell me the cosine of theta and the sine of theta. So since x tells me the cosine of theta, my x coordinate here is 1, so the cosine of 0 is equal to 1. And if the cosine of 0 is equal to 1, then I'm working over here with the absolute value of 5 times the absolute value of 5 times 1, which means I'm working with here 25. Well done, folks. Now this, you know what? Well done, us. I'll ask you to evaluate then the value of the dot product of v dot v. Try it out right here. Do your work. Pause the video, do your work, and then come back. Good. So we should be working right here. V dot v is in fact equal to 49. I believe the number I used up there was 7. Good job, boss. We're working with 49. Now, in fact, we might notice that this 49 and that 25 way up above, these actually have a very straightforward relation to what we were already working with, right? This is, in fact, equal to the magnitude of vector v squared. U dot u was equal to, this was equal to the magnitude of vector u squared. And that, my friends, is a conclusion that we can make that will hold true all the time for our dot product. If we're taking the dot product of the same vector, then we can just take the magnitude of that vector, square it. Lo and behold, we're going to be working with this frequently. Alrighty. Now let's keep going a little bit. Okay, so let's work with a third vector. A third vector is vector w. Now, if the magnitude of vector w is 4, and vector w is measured 30 degrees in between v and u. Okay, hang on. Let's go double check with our sketch. Way up here, we'll play around with it. I'm going to grab this and move it down. Good. Now I played around with my vector v. I made it a little more believable for a 60-degree angle. Good. Something like that. And then we'll draw a vector w 30 degrees in between. So I'm working with something right smack in the middle, something like this. And I know its magnitude is even less than that of vector v. We'll call this, again, vector w. Fantastic. Now what I'm asking you folks to find is the dot product between u and whatever vector comes from v plus w. Okay, well that might sound a little bit annoying. So let's play around with it. We grab vector w, we go over here, and we ask, okay, how can we find this vector? Well, this is simply an addition problem. You folks know how to work with addition. We're going to go something like that, and you folks need to find vector v, plus w. That's what we're working with there. And then we need to take the dot product of v dot w, a resultant vector up there, and vector u down here. You should be able to perform each of these steps. So the very first thing I'll ask you to do, folks, find v plus w. I'm asking you to find their magnitude. Try it out. You should be able to handle this. If you're not able to handle this, you need to return to section 6.2 when we went over vector addition. Yes, it is. Pause the video here and then come back when you've done so. Good, so we should be working here with, by using our cosine law, we should be working with this magnitude is, the square root of 41 plus 20 times root 3. So if I'm evaluating that there, bear with me as I bring that square root into play. So the magnitude of v plus w, there we are, is equal to the square root. Fantastic. Well done, folks. Okay, so if that's the case, then what we're asking you to do is to evaluate, remember what the question's asking us to evaluate, the dot product between u and this resultant vector that we just found right here. Well, our dot product, let's go, geez, we need to use a brand new color here. I don't know, we'll use brown. Sorry, folks, if if you dislike brown. That's okay. Then we're working, we need to answer u dotted with this resultant vector. And I'm going to write this one in pink, in purple, because that's what we've been doing so far. V plus w. Fantastic. Okay. So if I'm going to work here according to my dot product, then what I'm working with here, all right, well, I need the magnitude of u, and I need to multiply that times the magnitude of v plus w. And then I need to multiply that times the cosine of whatever angle is in between u and v plus w. And you know what, folks? I think this has been, just paused it for a moment just to verify. I think this has been a beneficial example for us to go through, at the very least, to get to here. I think at this point, honestly, it becomes a little bit more annoying, not quite worth our time, but we'll just put forth one last line here, because we honestly, it's just not worth our time to find this angle theta. I think then we're distracting from the point of the lesson here. But the magnitude of u, we know that we're working with here. Where is it? 7. There we go, 7 units. So we'd be working with the magnitude of 7 plus the square root of 41. Square root of 41 plus 20 root 3, all square rooted, times the cosine of this angle theta. Again, we're not going to find that angle theta. Nice try, folks. If you made it here, well done. That's good enough for me. All right, I might actually change the wording of this problem for you folks. Now, if we don't want to, if we end up at a problem like this, at an impasse where there's more work than we particularly care to do, that's okay. Because you might notice the last question was worded u dot v plus w. Now, what happens if we take advantage of some properties that we've learned about in the past? Well, right here, hang on, we could distribute, if we have some addition inside some brackets and some multiplication outside, we could distribute our first vector, in this case u, into those brackets, and we'd be working with u dot v plus u dot w, which both of these, remember, and this is kind of a key here, remember, u dot v, is that going to be a scalar quantity or a vector quantity? You might say, I don't know, Mr. Pasatka, this whole dot product thing, it's kind of confusing. I haven't seen it before. Let's take a look back here. Okay, we're working with a dot product is going to be the magnitude of AC. Well, the magnitude of AC right here, that's going to be a scalar quantity. The magnitude of AB, that's going to be another scalar quantity. The cosine of an angle, that's going to be a scalar quantity. We multiply 3 scalar quantities together. You've been doing that for years. That's like, I don't know, 3 times 4 times 1. Okay, that equals 12. That's a scalar quantity. There's no direction attached to that because there were no directions attached to any of these. So if we're working with dot products, we're always expecting a scalar quantity. So we're working here, and what we're actually really doing is we have one scalar quantity and we're adding another scalar quantity. We know how to do something like this. So I'll encourage you folks, try this one out. Try to evaluate u dot v. You should be able to do that. Try to evaluate u dot w. You should be able to do that according to the sketch we had up above, and see, folks, what this gets you. I will say when I upload this to the classroom, then the solution will be there. Fantastic. Now, if you're, I do encourage you, pause the video there, try that one out. But otherwise, if you're done that, let's move on just to some properties here. Then we have 2 more examples. I don't think we're going to go over both. I wanted to include both as an option, but that might take a bit too much time. So we're going to work here. Okay, so when we're using the dot product, a few rules are at play. Number 1, the commutative property holds true, and that means P dot Q is equal to Q dot P. Well, we actually saw that in play when we worked through example 1, A and B. We saw that vectors, that the dot product, the scalar dot product, U dot V was equal to the scalar dot product of V dot U. Fantastic. So we call that the commutative property. You've seen that before. Our distributive property also holds true. That's one that we're relying on in here when we're working with example 1F. Our distributive property means we can distribute a vector into a dot product, a first vector into a dot product or a second vector into a dot product, because this would also be equal to according to our commutative property, this would be equal to v plus w dotted with vector u. Fantastic. If you're not sure on that, pause the video, stare at it just for 10 seconds. It'll pop out at you. Well done. All right. Now, our what we call the magnitude property holds true. So you'll want to perhaps copy that down. Your magnitude property, which again, we found up above, that if we take the dot product of a vector with itself, then we end up with the square of the magnitude of that vector. And lastly, the associative property, which we've seen before. We can associate a scalar here, just a scalar. That's kind of key. We can associate this scalar however we would like into a dot product. So we could multiply it by the first vector p if we wanted to, or if we didn't want to put our scalar there, we could put our scalar right beside vector q. Or if we didn't want to put our scalar there, we could put our scalar on the outside and evaluate our dot product inside. And that might align with your understanding here, because if we're working with a scalar, that's just another kind of multiplication, right? So if we're multiplying, order does not matter. Fantastic. Alrighty. At this point of the note, I did want to sketch our cosine function. We actually did that earlier, so don't worry too much about this. But we'll work here with an example where we're taking advantage of one particular property. All right, so we have two vectors, and we need to be a little bit careful in here. The two vectors that the problem's asking about are not actually a and b. The two vectors that the question's asking about are vector a plus 2b and 3a minus b. All right, these are two vectors. Now, these two vectors are perpendicular, and we need to be careful. You may have read this question at first, perhaps if you read ahead, and you may have thought, well, okay, perpendicular, and I see two vectors a and b, so that means a and b are perpendicular. No, not quite. What this is talking about are the sums, the resultant vectors over here. These are the two vectors that are perpendicular. Yes, the questions are getting more complicated. That's okay. You folks can handle it. Now, we also know something about their magnitudes. We know the magnitude of vector A is twice the magnitude of vector B. Fantastic. And they're asking us to find the angle between vectors A and B, and they're giving us a bit of a hint. They're saying, hang on, just so you know, these two vectors A and B, these are not zero vectors. All right, so if these are not zero vectors, and we're told that these two vectors are perpendicular. All right, if these two vectors are perpendicular, let's keep in mind what that might tell us. If they're perpendicular, do we remember learning about anything perpendicular in this note already? Right here. If they're perpendicular, then our cosine of theta will be equal to 0. And if our cosine of theta is equal to 0, then our entire dot product will be equal to 0. So what that tells us right here is that our dot product is equal to 0. So our dot product between what? We need to be careful, not between a and b, but between these two resultant vectors. So vector a plus 2b, that's one vector, dot product with 3a minus b is equal to 0. Okay, what do I know about this dot product? Well, according to this dot product that I'm going to be working with, okay, hang on. Oops, we'll be taking advantage of our distributive property. All right, so I'm taking a dot product in here, and I recognize there are two terms in here, two terms in there. We've distributed something like this before when we were working with scalars that was distributing a binomial, or two binomials, right? So we're working right here, okay. If we're working here, we'll break it fully down for us, and that means we're working with vector A times dot product with 3a minus b plus vector 2b dot product with 3a minus vector b. Fantastic. So we can evaluate this a little bit further. We can distribute a little bit further because I have a dot product with 3a times a dot product with b. So I'm working with here, okay, a dot 3a plus a dot negative b, which allows us, if we want to, we'll be able to distribute this negative out. We'll get there. That's okay. We're following along. I'm hopeful. If you're feeling confused here, that's okay. At least I'm hoping you can follow along with the logic if you're not necessarily expected to be able to go through this on your own. So I'm working here, okay, so I can distribute this to b. So 2b dot product with 3a plus 2b dot product with negative b. Fantastic. Okay, let's get there. A dot product with 3a, well, hang on, that's going to be like 3 times a dot with a. How do I know that? Well, that's using my associative property, where I can take the scalar out. My scalar is a 3, and I can put that wherever I want to. So I'm going to put it on the outside, so I'll be able to evaluate a dot product afterwards. All right, and then same thing. I'm going to work here, and I will distribute this negative 2, or rather I'll move this negative as well over here. So I'm working with minus the dot product of a dot b. Fantastic, we're getting there. Here I have two scalars. I can multiply two scalars together if I want. So I'm working here plus 2 times 3, so that's 6 times b dot a. Oh, we're getting there. This is coming together so smoothly for us. Plus 2, oops, we're getting there as I'm making sure that I'm doing this right. Plus 2, and really we're taking both of our scalars here, so I have 2 and a negative. So I'm working with a negative 2. We'll subtract here. Subtract 2 times vector b dot product with vector b. Well done, folks. We're getting there. Okay, what do I know about a dot a? Well, I know I can use the magnitude property. A dot a is going to be equal to the magnitude of vector a squared. So I'm working here with 3 times the magnitude of vector a squared minus a dot b plus 6 b dot a. And hang on, I know, whoops, and I copied that wrong. I know b dot a is equal to a dot b. So let's just rearrange that. A dot b. Fantastic. I'm using my, my commutative property here. Minus 2 times b dot b, which is going to be equal to the magnitude of vector b squared. Fantastic. We're getting there. All right, so I'm working here. This is 3 times the magnitude of vector a squared minus a dot b, hang on, minus a dot b, that's minus 1 a dot b plus 6 a dot b. So I'm working together, that's minus 1 plus 6 a dot b, so that's plus 5 a dot b. So we were collecting our like terms there between these two terms. Fantastic. Minus 2 times the magnitude of vector b squared. Okay, well, hang on. What do I know about this a dot b? Well, I can evaluate this, what I'm working with here. Okay, so this is 3 times the magnitude of vector a squared plus 5 times a dot b. Well, what I'm going to be working with here is the magnitude of vector a times the magnitude of vector b times the cosine of that pesky angle theta in between the two. There we go, minus 2 vector b squared. Nice work. All right, we're nearly there. I'm hoping you weren't writing as largely as I was, but we're getting there. Then what we need to handle, okay, if we know the magnitude of vector a is equal to 2 times the magnitude of vector b, I could write this entire line in terms of vector b. So this is like 3 times 2, whoops, and let's put this whole thing in big enough brackets. There we go. 3 times 2 times the magnitude of vector b squared plus 5. 2 times the magnitude of vector b times the magnitude of vector b from above right here times the cosine of theta. Good work, us. Minus 2 times the magnitude of vector b squared. Nice work. We're getting there. We're almost able to simplify it here. I just need to square the end if I'm copying this over so that I don't run out of space. I apologize. I know you folks are able to fit yours in. Well done. I'm hoping you folks are. Nice work. Now we're able to, okay, we are so close. All right, so I'm working with 3 times, okay, if this entire thing is being squared, this is 3 times 4 times vector b squared plus 5 times 2, okay, so that's 10 times vector b squared. I should have my squared on the outside, not that it makes a difference. Times the cosine of theta minus 2, I need to square it up there, minus 2 times vector b squared. Oh, we're so close. All right, so I'm working with 12 times vector b squared, and I'm just going to rearrange this, minus 2 times vector b squared plus 10 times vector b squared times the cosine of theta. Well, here's the thing. I don't really need to care about my vector b squared. Let's collect our like terms. So we're working with 10 times vector b squared plus, and I got that 10 by collecting the 12 minus 2, right? Plus 10 times vector b squared times the cosine of theta. And sorry, I'll try and stay consistent with this. There we are. Now, let's keep in mind, what does this equal? Oh, right, this equals 0. And if this equals 0, I can divide both sides by 10. In fact, I could divide both sides by 10 times vector b squared. So I'd be left with 1 plus the cosine of theta, and that's the key. That's what we were looking for. So if 1 plus the cosine of theta is equal to 0, we can rearrange. So negative 1 is equal to the cosine of theta. If negative 1 is equal to the cosine of theta, what does that mean? Well, you could sketch yourself your cosine function if you wanted to. The only time your cosine function is equal to negative 1 is where theta is equal to 180 degrees, or theta is equal to pi radians. So therefore, answering the question at hand, theta is equal to 180 degrees or pi. Nice work. I'm glad if you stuck your way through that one with me. That was a nice, long, arduous example. Lastly, you know what, folks, because I think it'll be helpful for you and because this one will be considerably less painful, we're going to work in here and we'll take advantage of some of the properties we've already covered to show that these two vectors, that these two magnitudes are equivalent. The magnitude of v plus w and the magnitude of v minus w. So let's work in here. If I'm working with v plus w, then what I'm really looking at in here is v plus w. I'm working out, let's say I start here, then my resultant vector would end there. I'm looking at something like this. That's a resultant vector of v plus w. Fantastic. Okay, well, what I'm looking for as well is the vector v minus w. How can I find the vector v minus w in here? Well, I can go forward vector v, and I can go in the negative direction of vector w, something like that. So my starting point for my resultant vector is over here. My ending point is over there. Where I'm looking right here, I'm trying to find this cross. So what I'm really showing, what this problem is asking me to find is, or to show and to demonstrate and to prove that these two diagonals are equal. Now, if you know your understanding, if you have an understanding of rectangles, then you know that they're equal. That's great, but you're not able to prove it. You're not able to prove it, not yet. We're going to use our dot product to do so. So we'll work right here, and I'm hoping more so that you can follow than you can go through this on your own, but you will need to take advantage of approaches like this if you're going to be able to work through the practice problems. So if we know, we'll work here, if we know that the magnitude of v plus w we're going to be trying it out. So if we're going to assume, okay, first of all, let's assume that what they're telling us is true. If what they're telling us is true, all right, you know what, folks, I apologize for going all over the place here. This particular question, first of all, I copied it down wrong. Second of all, my voice is right near the end right here. I'm sure you've noticed. So we're going to leave this one. I will get there. If you're curious, you can double check the textbook at the bottom of page 375. But out of trying to respect my own voice, my own health right here, we'll call it for that video. I apologize for having this note done this way. I know this video was all over the place, but I'm hoping you're feeling a little bit more with your dot product. Well done, folks. You can take this knowledge into the weekend. If you were unable to make your whole way through this video, that's okay. You'll get some more time into next week.